Every diffusion sampler runs on a timestep grid, and that grid is your entire compute budget. Most samplers use uniform spacing or a handcrafted schedule like EDM's rho-7 or DPM-Solver's log-SNR mapping. But handcrafted schedules are tuned for specific benchmarks. A paper from Columbia and Hong Kong Polytechnic gives the first control-theoretic framework for learning the schedule. ART, Adaptive Reparameterized Time, treats the clock speed as a continuous control variable. The result, ART-RL wins all 62 result cells across 8 tables on CFAR10, MNIST, ImageNet, and 3 cross-dataset transfers by changing only the timestep grid. No weight updates, no fine-tuning, just a better schedule. The problem is Euler discretization error. The reverse time probability flow ODE runs backward from noise to data. Each step evaluates the score model once, so the grid spacing directly controls where your finite compute budget is spent. Uniform grids spread evaluations evenly, but early noisy stages tolerate coarse steps, while late data stages benefit from fine ones. Existing handcrafted schedules are rarely derived from a principled optimization. In a 1D analytical-score toy example, both DPM and EDM schedules actually perform worse than uniform, proving that handcrafted schedules fail outside their design domain. ART introduces a reparameterized sampling clock, T linked to physical diffusion time, tau, by a continuous map psi. The clock speed theta of T equals psi prime of T is the control. A uniform grid in T induces an adaptive non-uniform grid in tau. Local deceleration, small theta, gives finer resolution where the probability flow field is stiff. Acceleration elsewhere compensates. The objective penalizes a leading order, Euler local error, surrogate proportional to the stiffness indicator, Q times theta squared. Stiff regions with large Q force small theta, concentrating budget where error dominates. ART-RL solves this via a Gaussian policy with variance inversely proportional to stiffness. Theorem 1 proves the mean of the optimal Gaussian policy is exactly optimal for the original deterministic ART problem. On CFAR10 with HUN updates at NFE35, EDM's strongest reported configuration, ART-RL achieves FID 1.82 versus EDM 1.85. 3 matched 50,000 sample runs confirm robustness, ART-RL 1.82, 1.79, 1.82 versus EDM 1.85, 1.83, 1.85. At low budgets, the gap widens dramatically. At NFE5, ART-RL hits FID 130 versus EDM 305, a 2.3 times improvement. ART-RL wins every NFE column in both Hune and Euler configs. The 1D analytical experiment isolates pure discretization effects with a known score. ART-RL achieves the lowest Wasserstein, 2 distance at every single K value from 2 to 100. At K10, ART-RL hits 0.079 versus DPM 0.211 and uniform 0.114. Even at K100, with near-trivial error, ART-RL still edges out the others at 0.013 versus 0.027. Hand-designed schedules fail on this toy problem, validating the need for learned scheduling. The killer feature is transfer. The K18 CFAR10 schedule transfers without retraining across timestep counts via log linear resampling. It also transfers across datasets. A CFAR10 learned schedule dropped into AFHQ v2, FFHQ, and ImageNet 64 pipelines, replacing only the grid, wins all 18 cells, 3 datasets times 6 NFE values. On AFHQ v2 at NFE5, ART-RL reaches FID 195 versus EDM 266. The learned time parameterization captures a stable allocation pattern that survives grid resolution and distribution changes. It transfers across solvers too, from Euler to HUN to RK4, and across pipelines from EDM to EDM2, pixel to latent space. On MNIST, with a deliberately small 4.5 megabyte score model and RK4 updates, the schedule advantage grows even larger. At NFE9, ART-RL hits Linnet FID 3.62 versus DPM 334 and EDM 59.36. At NFE69, ART-RL reaches 0.98, all methods converge. A compact, less optimized score model benefits more from learned scheduling than a large, pre-trained one. ART-RL also extends to ImageNet 512 in EDM2, latent space, achieving FID 1.35 and inception score 284.4, both best in class. 3 honest caveats. First, at K2, meaning NFE2 or 3 depending on the solver, DPM and EDM are mathematically identical because both schedules pin only the 2 endpoints, sigma max and sigma min, so their grids coincide. This K2 degeneracy recurs across 7 of 8 tables. Second, the CFAR10 headline margin is razor-thin, FID 1.82 versus 1.85 is within noise on a single benchmark. The method's strength is consistency across all 62 cells, not a single large margin. Third, ART touches no model weights, only the grid, so it cannot compensate for a poor score model. It is a pure compute budget allocator. Don't handcraft your diffusion schedule, learn it. ART treats timestep spacing as a continuous control problem, wins every reported cell, and transfers across datasets and solvers without retraining. Change only the grid. Keep everything else. Subscribe for the next breakdown.